Hi there, and welcome from Ventura, California to today's webinar and virtual workshop, Beyond GNSS, a System of Systems, Testing Solutions for Autonomous Vehicles and Robotics, sponsored by InsideGNSS, Spirent, and Inside Unmanned Systems, and hosted by WebAttract, the leader in thought leadership webinars. I'm Lori Dearman, Senior Webinar Producer with WebAttract, and I'll be one of your moderators for today's session. And in just a moment, we'll be introducing our panel of thought leaders, as today's webinar is about hearing from these experts as they address the state of the art and science around testing solutions for autonomous vehicles and robotics. Now, we've invited you, along with over 350 professionals from around the globe, representing a variety of industries. And over the next 90 minutes, regardless of your industry segment or your location, we're confident that you'll find today's webinar of value. Before we get started, Richard Fisher, publisher, Inside GNSS and Inside Unmanned Systems, would like to take a moment to welcome you and introduce our sponsor and our moderator for today. So over to you, Richard.
Thanks so much, Lori. On behalf of the Inside Unmanned Systems and Inside GNSS team, I extend a warm welcome to our international audience for today's web seminar. We're delighted you can join us today. I'd like to introduce our sponsor, AJ Vemaru, Strategic Marketing and Business Development Manager for Spirent Positioning and Navigation. Hello, AJ.
Hello, Richard. Thank you. On behalf of Spirent, we'd like to welcome you all, and it's a pleasure to sponsor today's webinar. I'm sure you're going to enjoy the talk by the three top-notch panelists today. Talking about Spirent positioning solutions, you may know us as a GNSS simulator provider. This is something we have done for over 30 years and remains at the heart of what we do today. No one supplies more GNSS signals than Spirent does. What you may not know, however, is that in addition to the equipment, we provide test and evaluation services. And we're not just limited to GNSS. Increasingly, GNSS is used with other signals and sensors, which is not surprising. Spirent supplies test and evaluation solutions that provide coherent emulation of whatever combination of signals and sensors are required. To do so, we actually work with industry and academic leaders across the sector to provide integrated solutions. Our aim is to provide solutions to positioning, navigation, and timing test challenges that are realistic and support multiple signals and sensors beyond GNSS. We do this through internal development and by partnering with industry leaders and integrating with their solutions. With that said, I'd like to hand back over to Richard, and thank you all.
Thanks, AJ. We appreciate you sponsoring this today's webinar. And now I'd like to turn over the webinar today to today's moderator, Demos Gebra-Egziaber. Over the years, Demos has helped develop and moderate numerous Inside GNSS and Inside Unmanned Systems webinars. Demos is an associate professor of aerospace engineering and mechanics at the University of Minnesota Twin Cities. His research deals with design of multi-sensor navigation and attitude determination systems for aerospace vehicles. Recently, his work has focused on multi-sensor solutions for operations in GNSS stressed and GNSS denied environments, including the use of such systems on autonomous vehicles. Demos, thank you so much for joining us today. The floor is yours.
Thank you, Richard, and welcome to everyone again. Glad you could join us on this webinar. Before we get going, I want to give you a roadmap of sorts of what today's webinar is going to be all about. And we're going to be talking about ground vehicle PNT, and we have three panelists. And this slide here shows you kind of a generic picture for a PNT solution for the applications we're going to be talking about today. Our first panelist is going to be talking about the algorithms themselves and reliability issues associated with combining multiple sensors and multiple systems, and that's going to be Matt Spanko. Our second panelist is going to be talking about the overall system and is going to give an example of an actual system out there and how testing and issues that go into that are taken care of. And then our final panelist will talk about other sensors other than GNSS or other things that you could potentially use in a positioning solution for an automotive, for a ground vehicle application. So that's kind of a roadmap. So with that, let's go to a poll to start our webinar. Lori, if you could bring up the first poll.
Absolutely. Folks, coming up on your screen is that first poll, experimentally validating the performance of safety critical autonomous vehicle PNT system will require. And if you wouldn't mind going ahead and selecting one of the following responses: a month's worth of data, a year's worth of data, 10 years worth of data, can all be done in simulation. So looks like we have 1% weighing in with a month, 39% saying a year, our front runner there, 32% saying 10 years, and 27% saying can all be done in simulation. Demos, any thoughts there on the responses?
That's an interesting spread, and I think quite a few of our audience members are going to be kind of surprised by what they hear today from our panelists. So let's go ahead and dive into our first presenter, and it's going to be Matthew Spenko, who is an associate professor in mechanical materials and aerospace engineering at the Illinois Institute of Technology. Professor Spenko earned a BS degree in mechanical engineering from Northwestern University and a master's and PhD in mechanical engineering, both from the Massachusetts Institute of Technology. He was an intelligence community postdoctoral scholar at the Mechanical Engineering Department Center for Design Research at Stanford University from 2005 to 2007. Since 2007, he's been a faculty member at IIT. His research is in general area of robotics with specific attention to mobility in challenging environments and navigation safety. He's a member of the IEEE and an associate editor of the Journal of Field Robotics. His work has been featured in many popular media outlets such as the New York Times, CNET, and Discovery News. And examples of his work are on display at the Robot Revolution, a traveling exhibit currently at the Oregon Museum of Science and Industry. Matt, welcome.
Thank you. So before I begin, I want to just give a quick blurb about the Illinois Institute of Technology. We are a small private PhD granting institute just in the city of Chicago. You can see a picture of our campus right here, about 2 miles south of downtown Chicago. So I like to do that just because I don't think many people know exactly who we are. But on to navigation safety. So when we look at mobile robot safety, I'm gonna couch this problem in terms of, mostly in terms of self-driving cars, because that is where we're going to see most large numbers of mobile robots operating in the next 5-10 years or so. When we look at safety, we want to look at an overall safety risk. So on the top here of this chart, I'm looking at something that some regulating agency might want to set, let's say less than 1 fatal accident per 100 million miles driven. And down below that, we sort of have the 4 major components of robotics: path planning, the mechanical and electrical, control, and navigation. And so we need to look at sort of each one of these as pieces of our safety pie. Path planning is something that's being done, I think, by the major companies that are pursuing self-driving cars. This is how to get your robot from A to B. What do you do if a cyclist crosses your path? What do you do in traffic? Things like that. And that's not something that we are dealing with in my research lab. Mechanical and electrical, the next piece of that safety pie, is something that's taken care of mostly by the regulating agencies, and this is something that has been done for decades in terms of vehicles, airplanes, whatever it is. Manufacturers must meet certain standards in order to get their vehicles out on the road. Control is exactly what inputs you need to put into your actuators, your steering, and again, not something that we are entirely focused on. What we do in my lab is this last term here, this navigation safety or localization safety, identifying where the robot is in space based upon all of the sensor input and accounting for that sensor noise, and then also faults and specifically undetected faults that may exist in those sensors. Accounting for sensor noise is something that's been done for decades. We know how to do that well as roboticists. But what we don't know how to do well is account for undetected faults. These are faults that may occur in our sensors, but for whatever reason, we haven't been able to detect them and remove them. And when we look at our navigation faults, we're looking at sort of, these are all coming from our raw sensors. And these sensors here are down in the bottom level. So these might be our GPS sensors, our IMU, that's our initial measurement unit, and then our raw LiDAR, so I have laser here, laser rangefinders, radar, camera, errors and faults. These are range-based sensors. And then we have odometry, errors and faults. So these might be odometry that you would get from your wheels, or they also might be odometry from LiDAR point clouds, for example. But what's key here is sort of this third term here, these range-based sensors, these LiDARs, radars, and cameras, errors and fault. And the thing with these is that they don't give us any actual position. What we need to be able to do is we need to be able to extract features from that data and then associate those features with a landmark. So this sort of middle term here, this feature extraction, data association errors, these are algorithms. And this is where we spend most of our time, is trying to analyze how these algorithms play, how these algorithms introduce faults into our navigation safety. And then over on the right-hand side here, we have landmark database errors. Obviously, the map that you have of your landmarks may contain errors, but again, we don't really focus on those. We really focus on these terms in the light blue boxes right here. So one of the things that we want to ask ourselves is, before we go off and do any analytical work, is can we do this all experimentally? And there's a lot of different analysis done on this. I'm presenting some work done in 2016, and the authors posed the question, how many miles would have to be driven without failure to demonstrate with 95% confidence that the failure rate is less than the current failure rate or 20% better than the current failure rate? And the failure rate I'm talking about here is fatalities, automobile fatalities. In the US alone, it jumps between about 35,000 and 40,000 auto fatalities per year, and about 90% of those are attributed to human error. And when you look over on the right-hand side here, you see these large number of miles here, 275 million or 11 billion miles. These are huge numbers. And when you look and see what the manufacturers are doing, we're not even close. So I think Waymo just announced a couple, maybe last month ago, that they're up to about 8 million miles driven, which is extremely impressive. And there is, so I don't want to take away from that. But even if you don't agree exactly with these authors' analysis, you're still looking at orders of magnitude difference between what we're able to achieve and what we actually need. And the real kicker here is when you want to prove safety, when you want to improve it through experimental work, you can't make any changes. So anytime you make a change to your algorithm or you update your sensor, you've got to start that clock over again. So instead of doing that, what we're looking at is taking inspiration from the aviation industry. So I don't come from aviation and the navigation safety community. I come from a robotics background. My collaborator comes from the aviation side. So we're looking to take inspiration from him and look at guaranteeing integrity, which is a measure of trust in a sensor's information. So there are some distinct difficulties in adopting aviation safety methods to terrestrial robots. So up here on this chart, I have an example of what we're trying to do here. We have a robot on the left that's our current time pose. Pose is position and heading. And on the right, we have some future. We're going to predict our pose into the future. And then we have an alert limit requirement box. And so basically what we're trying to ask ourselves is, what is the probability that our future pose is going to lie outside of that alert limit requirement box? And for a self-driving car, this might be, let's say the lateral layer might be the size of the lane that you're traveling in. And so we have sort of three unique challenges here when we're trying to adopt these aviation standards or aviation techniques into ground robots. The first one is that GNSS alone is insufficient. We are going to be operating in a lot of GNSS denied areas, and thus we need the multi-sensor system, the sensors that I talked about a couple slides ago. The second one is that in aviation, our integrity risk peaks at landing, and that is no longer the case. We now need to have continuous risk monitoring for terrestrial robots. The last one is that we have unpredictable measurement availability. So in aviation, you're landing on well-defined, carefully maintained airports, and that you can control the environment extremely well. In mobile robot applications, we need to operate in a dynamic environment. We have construction that's going to be going on. We have people walking in front of landmarks and features that we want to extract. We have other cars, we have cyclists. So we have all these sort of dynamic moving environment that we have to account for. So to give you an example here of what I'm talking about with feature extraction and data association, this is just a simple test we've done. On the left-hand side, we've got a little cart that has LiDARs, a couple LiDARs, GPS, inertial navigation system on it, and it's being pulled around in a field with a number of trees on there. And on the right-hand side in this video that's playing is you can see the LiDAR point clouds, and then everything that's popping up in red is a feature that we've extracted from the environment. And so these are going to be associated with those trees that we have there. And you can see some of these things, you can see these features are popping in and out depending on the data frame. As this vehicle moves around, these features are moving in and out of our field of view. So a lot of challenges just in that. So what are some of the faults, though, that might occur in feature extraction and data association algorithms? Well, basically we call them landmark faults, and we can break them down into two different categories. The first one is a feature fault, and this means that a landmark is associated to a wrongly extracted feature. On the right-hand side here, I have a picture that I took from my car in downtown Chicago. So this would be a very difficult scene for a self-driving car to operate in. You can see that because we have our L tracks are overhead, and even if they weren't there, we'd still have the tall buildings, which would create a GNSS denied environment. But we also have construction, a lot of cars moving on. And so when we take a look at these feature faults, you can see one example of them might be that we have some obscured posts that we'd want to extract, that we'd expect to be there, but we have all this construction on the right-hand side. So these might cause a possible feature fault. The second type of landmark fault is a misassociation fault. And that is a landmark is associated with a feature correctly extracted from a different landmark. So an example of that might be these posts that are too close together, and this could cause a misassociation. All right, so how do we evaluate the probability of hazardous misleading of misassociation? Well, we're looking at our like I talked about before, the probability of being outside that alert limit box. We evaluate it under fault-free and incorrectly associated conditions. Now, I'm going to throw a couple equations up here. Don't get thrown off by them. We're going to look at a couple terms here and see what we're going to tease out of them. One of them is to abound our probability of hazardous misleading information is this term on the right, which is set by some safety requirements, some regulating agency. And then we have two terms here. One is we can solve from our Kalman filter covariance. The second one is the key though here. This is trying to identify what is the probability of making a correct association with these landmarks. And to do that, we actually have a really nasty equation here, but I want to point out again just sort of two things. One is that this number of landmarks in the field of view, and we have this interesting dichotomy here because in one sense, the number of landmarks is worse. In another sense, we have more landmarks being better. And this last term that we have to look at is accounting for the separation among landmarks. And so basically what we want to have is a large number of well-separated landmarks. If the landmarks are too close together, then our probability of correct association actually goes down. So that's not good. So we have to sort of balance these off. So a lot of things that we do is we're doing this work. This is an example of a vehicle moving in a simulated environment, and we're picking off features in the in the environment. We're picking off these sort of landmarks, these poles right here. And I want you to look at two of these lines over on the right. The two lines that I want you to look at are the solid lines. The one in red is what happens if we calculate our hazardous misleading information with no landmark selection. This means that we're just accounting for every landmark that we see in the environment. At this time epoch, about 42 or so, you see that our probability of hazardous misleading information goes extremely high, and we would have to cease operations. But if we look at this line in blue here, the solid line blue here, we're actually calculating our probability of hazardous misleading information while accounting for landmark separation, and we are then able to lower our probability of hazardous misleading information by essentially throwing out landmarks that aren't well separated. So in conclusion, this integrity is important for this idea of ubiquitous robots. As we get large numbers of mobile robots like self-driving cars operating among humans in these safety critical operations, we're going to need to account for integrity and really look at the situations where we have undetected faults. Mostly what we're focused on, my work focused on, is incorrect associations between features and landmarks. And that requires us to find landmarks to be plentiful. We have to have them there, but they also have to be well separated, and then we have to be able to remove those separations. So to finish off, I'd just like to acknowledge my students in my lab, especially Guillermo Arana, who most of this work is based on, as well as my collaborator, Professor Matthew Yoger at the University of Arizona. So now back to you, Demos.
Thank you, Matt. All right, so let's move on to our next panelist. Our next panelist is Curtis Hay. Curtis Hay is a technical fellow at General Motors. In this role, Curtis develops precise GNSS and map technology to enable safe and reliable operation of autonomous vehicles. Curtis also led the team responsible for launching GM's 4G LTE connectivity in North America, Europe, and China. Prior to joining General Motors, Curtis was an officer in the U.S. Air Force for 8 years, where he developed GPS technology for precision weapons, performed satellite launch planning, and managed the GPS Accuracy Improvement Initiative. Curtis also developed precision GPS equipment to automate farm and construction equipment while he was at John Deere. Curtis, floor is yours.
Well, thanks for the introduction, Demos. My name is Curtis Hay, and I'll be building on some of the robotics principles that Matthew described in his slides from the Illinois Institute of Technology and how we apply those principles in the automotive industry. So our mission and vision within General Motors as a global car maker is really summarized in this slide. When we wake up in the morning and commute to work, these are the thoughts that drive us and motivate us in this rapidly changing world of automotive transportation. We have a vision of zero crashes, and robotic principles and autonomous vehicles factor into that. We have a vision of zero emissions, so we'll continue to invest and lead in electric vehicles. And we have a vision of zero congestion. So as the world becomes more urban and greater dependence on ride sharing becomes more pronounced, GM's committed to being a part of the solution for the 21st and 22nd centuries. So I wanted to do a survey here of sensors that are found and used today on autonomous and semi-autonomous vehicles and talk a little bit about the pros and cons of each of these sensor types. So at GM, we view sensors really in two categories. We have perception sensors that use remote sensing capabilities to localize a vehicle in a relative sense. How far away am I from a curb or a stop sign or an intersection? We solve that problem with radar, LiDAR, and cameras. And then we've got another classification of sensors that are responsible for positioning the vehicle in an absolute sense with respect to a well-established reference datum such as WGS84 or ITRF 2000. Where is this vehicle on planet Earth with a prescribed latitude, longitude, and elevation? And we perform those functions with high definition maps, with motion sensors such as gyroscope, accelerometer components, wheel ticks, and of course GNSS. GPS, GLONASS, Galileo. A few years, I would say 18 to 24 months ago, there was a debate within the automotive industry about which class of sensors was more important. And what I've come to realize and what we've learned at General Motors is it's really not an appropriate question. And what we've come to believe now and are committed to is we need all of these things. There is value in purpose and relative positioning, a vehicle with respect to known landmarks and objects on the roadway, and there's high importance in absolute localization. Where is this vehicle with respect to a map that gives us a good perspective of the road ahead? So radar, we'll go quickly through these columns and tables, columns and rows. Radar is relatively low cost. It's a proven technology and it has good ranging accuracy. Unfortunately, radar is not good at detecting road markings such as paint stripes or shoulder markings. LiDAR is a highly effective sensor for localizing a car in a relative sense, ranging measurements which are effectively reflected returns of radar, of lasers, where we can look at the reflected intensity and range of return of the signal, provides highly accurate ranging, typically to within a few centimeters. LiDAR suffers today from high cost. It's less effective in areas with lower feature density. You know, Matthew talked about spatial distribution of objects and landmarks along the road and the importance of having those landmarks spatially separated from one another. If your environment doesn't meet those criteria, the value of LiDAR tends to go down, such as in deserts or open highway conditions. Camera is a wonderful sensor. There's been a lot of investment in the auto industry over the last several years on improving and optimizing camera video. Cameras today are typically lower cost. They perform a good job of object detection, recognizing what you're looking at, whether it's a road sign or a parking meter or a lamppost. Again, cameras tend to be less effective in featureless areas and suffer from performance degradation in weather conditions, snow, rain, fog, darkness. So we like to complement the first three rows with sensors on the bottom three rows. We've found at General Motors, and we've publicly advertised our excellent map that we use today for our Super Cruise vehicle. I've got a slide on that later. Our audits of the absolute accuracy of our map demonstrates that we typically achieve less than 10 centimeter accuracy with 95% confidence. There are downsides of a high definition map, typically stored as a database in a production vehicle, and that would be these maps require continuous updates. Roads change, construction happens, and we need to keep up with that. And it tends to be a higher cost sensor when we're performing the acquisition of data. When we're performing precise RTK or LiDAR road scans, that takes time and money, and that needs to factor into the business equation. Motion sensors are quite low cost. The quality of MEMS sensors has gone up significantly in the last few years. That trend is continuing, but we still suffer from a higher drift rate than we would like for microelectrical mechanical sensors such as gyroscopes and accelerometers, but that problem continues to get better. And then this audience, of course, is familiar with GNSS. We're in a period really where we have an embarrassment of riches. We've got the American GPS system, we've got the Russian GLONASS constellation, the Europeans continue to invest in Galileo, the Chinese have continued to invest in Beidou. These components on a car typically have lower costs and global availability. As Matthew mentioned in his presentation, GNSS suffers in urban areas and tunnels, and these are areas where customers are not going to be forgiving of issues with autonomous vehicles. So we need to complement the weaknesses of GNSS with the other sensors on this slide. So this is a pictorial view of how we fuse information from these disparate sensors into a combined solution. So on the left side, I've grouped again our perception sensors, LiDAR, camera, radar. On the right side, we complement those relative positioning sensors with absolute localization sensors, including GNSS, inertial measurement units, and a precise map. If we go counterclockwise here, LiDAR, as I mentioned before, is characterized by creating a point cloud picture of your surrounding environment using laser returns, where we look at the reflected intensity and range of return of those signals to construct an artificial reality. Cameras are similar. Camera can perform signal processing to identify object data, such as paint stripes or road signs that can be cross-checked against a database of those objects stored in a map. And then radar is an excellent sensor for long-range and short-range detection of both permanent and stationary objects. On the right side, I've spent a lot of my time over the last several years improving GNSS. What we've learned here at General Motors and what we've publicly advertised is our ability to achieve more precise localization by applying corrections. So our Super Cruise vehicle, which I'll show a slide for, achieves superior location performance by applying real-time clock, orbit, ionosphere, and troposphere corrections to the raw observables that we receive today from 2 constellations. We combine those raw measurements from space with motion sensor information from the car, such as yaw rate, X, Y, and Z, acceleration and displacement values, as well as roll and pitch. We localize to a precise map, meaning we use information from all of these sensors on a production vehicle to identify where we are in an absolute reference frame. Typically WGS 84 or ITRF 2000 are common, and that gives us the ability to locate the vehicle with a precise latitude, longitude, and elevation. So when we know where the car is, that allows us to perform the control functions such as path planning, trajectory control, steering, and braking, those functions that are a critical part of any autonomous car. Demos, back to you in the Twin Cities.
All right, thank you, Curtis. All right, so at this point, we'll switch over to a short Q&A session. So if you have questions, please send them in, and we'll try to answer them or try to get to them on air here. So with that said, let me start out with, I guess, the first question. Actually, this would be for you, Curtis. So now that we are seeing all these different sensors that are going to be integrated into an automotive system, do you think this is going to change the relationship between OEM, sensor suppliers? Do you think it's going to lead to more vertical integration, say like we see in the cell phone market, as opposed to horizontal integration that is, I guess, common today?
Yeah, that's a great question, and it's a question that I live every day at work. So what I see happening every day as this industry evolves is the gap between innovation, coming out of our universities and startup companies throughout the United States and production is narrowing. So what that forces me to do, what that forces us to do that make technology decisions within the automotive industry is to be creative with how can we get involved early in sensor development, sensor qualification, testing, the business of bringing new technologies and new sensors into the domain of autonomous vehicles so that we direct where we're going more ourselves and rely less on our typical partners, the typical tier 1 manufacturers that we think of, where the automaker now is calling more of the shots and directing the vision of product development. So I think it's a good trend. This technology evolves quickly, and our role in the automotive industry is to not be left behind or to be late. So for my part, I appreciate the pace of innovation and appreciate the challenge of taking advantages of innovation at the first opportunity.
All right, thanks, Curtis. Matt or Chaminda, I guess the third panelist that I haven't introduced yet, anything you think you'd want to add to that comment or any insights? I guess that's a no.
You said it well.
All right. All right, so moving on. Next question. This one is for you, Chaminda. Again, I haven't introduced you yet, but it kind of seems like it's dead on to what you're going to be talking about later on. And I don't want to steal all your thunder, but I'll ask the question. Are there, I guess, as industry or folks interested in this whole area of autonomous vehicles, are there other sensors, like absolute sensors, that they may be considering or pushing for as one of the solutions to be considered in this problem?
So related to connected vehicles, the question is about absolute sensors using transponders or anything like that to aid in this process. There's U.S. government working on trying out connected vehicle technologies in this respect. So that work is going on. From our perspective, we have the ability to enable positioning in very challenging environments, and we'll talk about that in my section. Actually, that's all I can add to it.
Okay. Again, the audience that asked that question, you will see that Chaminda's presentation will actually directly answer some of those aspects of that question that you asked. All right. So moving on to the next one. Let's see. This one is going to be for you, Matt. And so, in addition to the three key differences you noted between aviation applications and ground vehicle applications, can you comment on a few more? I mean, what are there more differences that you see between the aviation safety aspects and the automotive aspects of things?
Well, perhaps I can comment on one of the big implications of those differences, and one of those is that one of the things is that prior faults are going to impact our current time safety. And what that means is that if we do not have periodic updates from some absolute positioning sensor, it is going to be our probability of hazardous misleading information, our integrity risk, is going to grow over time as we travel through a city. So you can imagine a vehicle starting out at one end of a city and not having a GNSS signal or some other type of absolute positioning signal. As it drives through that city, its safety risk is going to grow and grow and grow and grow unless it gets something. So some type of absolute positioning. So it's going to make us think about what other type of sensors we can add into, or how often do we have to add into these environment, or how do we have to change or modify our transportation infrastructure to account for these and really deal with safety.
All right, thank you, Matthew. All right, so let's move on to the second half of our webinar. Before we do that, we'll start with a quick poll. So Lori, if you could bring up the poll.
Absolutely. On the screen, we've got that second poll. Compared to aviation systems, the reliability requirements of PNT systems for autonomous ground vehicles are expected to be more stringent, less stringent, or equally stringent. All right. Well, what do you think there, Demos?
All right, and I guess, well, after Matthew's presentation, I think folks are seeing how challenging it could be for the automotive applications, and I guess a lot of them show that it'd be more stringent. So kind of interesting. All right. So with that, let's move on to the second half, and I guess I'm going to give the floor back to Curtis to tell us a little bit more about the practical considerations for test and development. Curtis?
Okay, very good. I tend to agree with the choice of our audience on that last question. It's a demanding environment to be operating in for an autonomous vehicle. So let's talk a bit about connectivity. So Matthew mentioned the importance of keeping our sensor information fresh, keeping our map updated. So there's an important role to play for connectivity. So a vehicle such as Super Cruise, which I'll describe on the next slide as an example, these are all functions that are enabled by either 4G, LTE, or some other form of cellular communication space. That can either be raw satellite measurement information or delivery of corrections, or Wi-Fi for offboarding or receiving large amounts of data for autonomous vehicle purposes. I mentioned earlier, GNSS corrections are a really important part of maintaining a low probability of error and high accuracy required for absolute positioning. We receive today for Super Cruise those corrections through mobile IP and allow us to remove many of the effects of clock orbit and weather effects. As we continue to improve our localization ability, the importance of corrections will continue to be an important factor. Precise map updates, I mentioned earlier as well, that the moment a map becomes part of a database in a car is the moment that it's out of date. Construction's dynamic, road changes happen, and we need to be able to update that map quickly. So we do that today through cellular with periodic and recurring map updates. And that won't be possible, of course, without connectivity between the car and a back office. Remote diagnostics is an important capability for continued engineering improvement. So as an autonomous vehicle is driving and is being operated, we need to collect health information of the systems on the car, relay that back through telemetry to a repository that allows us to monitor and improve autonomous functions. Over-the-air software updates. Vehicles are a complex combination of many different electronic control units that all operate embedded software. Software is not always perfect, and we need the ability to update and fix bugs as well as continue to make performance improvements, and that's enabled through connectivity. At General Motors, we've got a long legacy of providing advisor services. We do that through our OnStar brand. Those advisors are useful for emergencies and to provide peace of mind for both our traditional vehicles as well as the new frontier of autonomous and semi-autonomous cars. What I don't show on this slide is vehicle-to-vehicle communication. That's another important and emerging technology area where GM and our competitors and partners are continuing to invest. So I would add V2V communication as an important enabler for services as well. I mentioned a couple times Super Cruise. I'm really proud of the work that we've done here at GM and within my team specifically for Super Cruise. This is a Cadillac CT6. We launched Super Cruise on this vehicle in the fourth quarter of 2017. It's effectively a hands-free lane centering capability on highways in the United States and Canada that have been precisely mapped. It's an optional feature that a customer can purchase at a dealership. It's specified to operate between 0 and 90 miles per hour on interstate highways. And an important point is the driver attention is required. We've got a driver monitoring system that we're proud of that maintains a connection with the driver, makes sure the driver is paying attention, looking out the windshield, is engaged in the hands-free experience. And if that driver looks away or is not paying attention, we'll prompt the driver to retake control of the car. This is not an autonomous vehicle, it's NHTSA level 2, but many of the same sensors and sensor fusion tasks that are performed for this vehicle are common with autonomous vehicles both inside and outside of General Motors. So let's talk about some of the challenges that we continue to deal with within the automotive industry. And then I'll end my presentation with a slide on testing and simulation. So precise localization within a geodetic reference frame, where we can align latitude and longitude and elevation with known truth, requires a precise map. Today we do manual surveys using RTK and LiDAR of roadways across the continent and around the world. That's a great process, but it can be slow and somewhat inefficient. We know we need to transition to a crowdsourcing model where vehicles can independently send camera, potentially LiDAR, and GNSS information to the cloud, where we'll construct precise road segments and deliver that back to the car. There are a lot of startups, there's a lot of innovation occurring at universities and around the world in that area, but it's not mature yet. And there's a lot more work that needs to be done before that's ready really for production vehicles, but these events are happening. High accuracy GNSS will continue to be important. There are ways to improve that by combining satellite and IMU data with camera information, for example, in a tightly coupled filter, and we're working on these concepts as well at GM, and we can really draft off of the great work that's being done by IMU manufacturers. I continue to be impressed by the innovation and forward thinking of MEMS sensor manufacturers around the world. Efficient testing is an important part of autonomous vehicle development, so I'll talk about that on my final slide. I tend to agree with the audience perspective that we have to continue to drive, but we also need to use hardware in the loop modeling and simulation where it makes sense. So if we can construct a realistic representation of a car using simulators for camera, LiDAR, GNSS, and vehicle motion, we can take advantage of that capability to limit the need for us to spend a lot of time on the road. We will never replace real road time, but we can also be more efficient if we make clever and creative use of test equipment. So that concludes my portion. So back to you, Demos.
Thank you, Curtis. All right, so let's move on to our next panelist, who will, I guess, talk about other sensors that could be used in this application. And our speaker is Dr. Chaminda Basanake. Chaminda is a principal engineer with Locata Corporation, where he is responsible for taking the Locata technology to new markets for seamless machine automation, autonomous driving, and asset tracking. Prior to that, he was a senior engineer with General Motors R&D and GM OnStar, where he served as a GPS GNSS subject matter expert for GM and the U.S. DOT Automotive OEM Collaboration Crash Avoidance Metrics Program, or CAMP. He has co-authored over 20 GM patents and numerous publications and presentations on GNSS, connected vehicles, telematic systems. His career highlights include winning the GM's highest award for excellence and being nominated as one of the 50 leaders to watch in the GNSS industry by GPS World Magazine. With that, I will give the floor to you, Chaminda.
Thank you, Demos. I would like to thank Spirent and InsideGNSS for giving us this opportunity. So I'm going to talk about a technology called Locata. We call it your own GPS. And my objective will be to show you why we think that. So some of you may have heard about us. If you haven't, we've been around for quite some time. So this is an article from 2015 from Inside Unmanned Systems magazine. We've been enabling autonomous control of machines and vehicles, in this case, particularly land vehicles and targets in controlled environments. We've been enabling precise positioning of those for quite some time. So you'll hear more about what we do and how we can work as a part of a system, as a sensor, with my presentation. So we are a ground-based transmitter system. We work very much like GPS, your own local GPS, we would like to call it. We deliver RTK level performance, centimeters in open sky, and even indoor and severe multipath environments. And we can do the same thing with GPS jamming and spoofing. We can work as a core system in a system of systems, as you will see in my presentation. Or we can work as an augmentation to other GNSS as well, much like a part of any, much like a constellation in GNSS. We work in several industry segments. You will hear about these, mainly in automotive safety testing, in vehicle positioning and control, port automation, and we are also in mining and military industries as well. So some basics about the technology. our system is designed as a ground-based line of sight system. So some of the requirements for GNSS to have this line of sight visibility, they apply to us directly as well. But given we are a ground-based transmitter system, we can customize the accuracy and reliability, and our performance does not change with time like the satellites that move around. We transmit our signals at 2.4 gigahertz in the current system. Again, being a ground-based system, we can transmit much stronger signals. That gives us more immunity for jamming and other cases. And for our transmitters, we can transmit up to 4 signals. So they are GNSS-like signals with ranging information and nav data. And the other important aspect is our system is, all the transmitters are time synchronized, but we don't use atomic clocks. We do have a proprietary technology called time lock. So basically we can, if you look at the network here, we can designate one of the transmitters, let's say the leftmost transmitter as the master, and then we can configure the other transmitters to listen to the master, and just using the ranging signal from the master transmitter, or the localite we call them, we can get the others to time synchronize down to nanosecond level. So this is how we time synchronize the network. You can see a picture of a transmitter and a receiver in that slide. And another thing to add is if we bring in a GPS receiver as the time source that can be attached to a master localite, then we can time synchronize the whole network to GPS. So we can operate in the same time scale that way. From the receiver point of view, we are just like any other GNSS receiver in many respects. So we output the same kind of data, function the same way, with the important exception that we can deal with severe multipath and indoor environments even. So we'll talk about that in more detail later. So let's start with an example where we operate standalone in automotive safety testing. So this is the Insurance Institute for Highway Safety, or IIHS. They are, as most of you probably know, they are one of the 2 organizations in the US that rates crashworthiness and safety features of all the new cars that enter the North American market. So they have 2 test tracks, an open track that we've been operational since 2016. And they built this cover track that you see towards the right-hand side of that aerial picture. That's 5 acres under this giant dome cover. They don't have RTK, GNSS RTK service availability down there because of the sky visibility limitation. So we've been operational down there since the beginning of this year. We've been there before, but we did some validation tests, and we've been officially operational since the beginning of this year. So when IIHS found out that they cannot use their standard equipment, they came to us looking for a system that can service both service tracks, test tracks, and that's how we started working with them. We deliver better than 10 centimeter accuracy at 95% in both of these tracks. And we also deliver very high repeatability and predictability. That's something they wanted as a very important characteristic of the system. When they're testing, let's say, 2 models of 2 cars from 2 makers, they want to have ideal identical test conditions, and that's what we deliver. Because our satellites, our localites are stationary, we can guarantee the performance over time. And also our equipment is pretty much plug and play, ready, can be swapped with GNSS equipment. And that's important as well. They can bring in any other control or equipment that works with GPS, and they can just plug in our receiver and it works the same way. They use our system for test vehicle and target positioning, tracking, and control. These targets could be robotic platforms with dummy vehicles, pedestrians, and cyclists, and so on. They also do automated path following, and we'll talk about that in a little bit more detail in a slide that's coming up. Here's a quick view of the network. We have 16 transmitters there in both tracks. You can see a closer look of one of the towers on the left-hand side. That's one of our localite transmitters. And the blue overlay you see is the DOP value. by design. So given we have fixed transmitters, we can estimate that and also estimate the reliability and guarantee that that performance. So at the late last year, we did a demo for IIHS with our partners in automated path following, and so IIHS is in the process of automating some of their driving tasks because they want to take the driver dependency out of some of the tests. For example, you can imagine if you want to drive a car a certain path and repeat it exactly the same way, it's really hard for a driver to do that. And these systems allow them to do exactly that. They can record scenarios, replay them over and over again with different settings if they want to. So that's exactly what we did. In this case, Anthony West Dynamics, one of our partners, they brought in their steering robots and brake and acceleration control robots, as you can see in the pictures. They were installed in a car, and our receiver, which looks like a RTK quality GNSS receiver, outputs 10 Hertz data to Oxford Technical Solutions GNSS INS integration unit. It's the same thing as a GNSS INS unit for us because we output NMEA data. We can output other formats just like a GNSS receiver. So they would take that, output 100 Hertz data for the controls of the AB Dynamics steering robots and control robots. So here's a closer look at one of the test drives that we did. So in this case, we call this the double lane change maneuver. So the vehicle comes in the far lane, changes lanes back and forth real quick. So this was recorded. This was done in the covered track where no GNSS is available and only locator service is available. So what was done here, this drive was manually driven and the barriers were placed only 6 inches away from the side of the car on both sides. And then that recorded scenario was replayed 48 times at different speeds, ranging from 10 to 45 kilometers an hour. And you can imagine a human driver trying to go through these barriers at 45 over and over again. And we were able to show after 48 repetitions that the locator system accuracy itself is plus or minus 3 centimeters at 95. And the system, the overall system with the controls that was able to repeat everything down to 6 centimeters. So that was just one of the scenarios. We did different other drive scenarios that are useful to IIHS, and we were able to show that same accuracy and repeatability can be delivered anywhere in both tracks. So here's another example, but in this case, locator is working as an augmentation for GNSS. So deep pit mines, especially when the machines are operating close to the wall, it's like an urban canyon. They have visibility limitations. That brings the accuracy down, and that limits the number of hours the machines can be operated autonomously or precisely. And that's where this product came in from Leica, JPS. It's basically a Novotel GNSS board integrated with a locator receiver in one enclosure. With this, all they have to do is take one of the solar-powered portable units that you can see in the right-hand side photo to the top of the pit, and then start broadcasting locator signals down into the mine. And that gives more signals as well as better geometry. And they were able to show that service availability has gone up from 75% to 98%. Let's look at a more complex environment and see how we deal with multipath. And as you all know, multipath is a huge problem, especially in environments like this. So I'm showing only some reflections of a transmitter, in this case, one of the local lights. And as you can imagine, there can be millions of reflections. And this is one of the big problems in this environment. Now, with over 10 years of R&D, we have come up with a new technology called V-Ray. It's a collection of patch antennas, but this special antenna works with our standard receiver. And what we can do is we can sequentially sample these antennas and then basically create a beam. We call this correlator beam forming. We can create millions of these beams, and then we can scan the environment, identify the direct signals, and only track the direct signal. This allows us to deliver centimeter level accuracy in these environments. And this is a proven technology, as you will see in the next slide. And the other important aspect I would like to bring up to the audience is that this is applicable to GNSS multipath mitigation as well. The US Air Force Institute of Technology has done a study, and they have shown that it can be applied equally well for GNSS. So Locata is a big part in a wave of port technology automation that's happening around the world. A big part of that is automating these machines that you see on screen. The blue machine, it's a straddle carrier. This particular one is from Kona Cranes. These are level 5 automated machines operating fully autonomously without even a crew cabin. And these can operate side by side with manually operated machines and can travel up to 40 kilometers an hour. And they can stack up to 4 containers, as you can see. So we enable all of that with our positioning technology. We deliver 3 centimeters at 95 with our V-Ray technology in this very cluttered environment in terms of multipath. We're becoming pretty much a standard technology, working with multiple OEMs. And other logistic operations will follow after this automation is in place. On top of giving the operators unprecedented accuracy and reliability, we also give them flexibility. So in this sort of an environment, they have tried GNSS, other sensors like embedded sensors, markers, and so on. And they've found out that multipath is a problem for GNSS, and other things can limit what they can do in terms of infrastructure changes and so on. So we give them the flexibility to modify paths, change anything within the service area, and more importantly, we enable them to do conversion to automation in a running port without stopping operations. So that's a really important thing. They don't have to tear up infrastructure, put new markers, or change things. Once the transmitters are in, they can bring in machines and start changing things as they wish. The first of these ports will come online, will be commissioned at the end of this year in New Zealand, Auckland. Sorry, Port of Auckland in New Zealand. Here's another quick look at another place where we operate. We are at the White Sands, US Air Force White Sands missile range. They have a 1,200 square mile network that we cover, and this is used for GPS denied tests and so on. And we are the core non-GPS sensor in the ultra high accuracy reference system, and we've been operational in this network since 2016. Finally, I want to wrap up with this. So with the infrastructure, you can see how we can enable all of these new things in mining and other industries and ports. And then we're working on getting our system to be frequency flexible, and then integrating with GNSS to reach new markets. And of course, we see a lot of potential in using our technology on particularly correlator beamforming for GNSS, and of course, time lock for time synchronization for applications like even autonomous vehicles and connected vehicles further down the road. Thank you, and back to you, Demos.
All right, thank you, Shaminda. All right, so before we head on to our last Q&A, let's do a quick third poll. If you could bring that up, Lori.
Sure will. And on the screen is that final poll. The question there is, in addition to GNSS and other sensors for absolute localization, what are the most important perception sensors for autonomous vehicles? And in this case, although you can select multiple options, we're asking you to select your top 2. So it's kind of on the honor system. If you'd give us your top 2 choices among radar, LiDAR, camera. 30% saying radar, 70 LiDAR, and 74 camera. Any thoughts there, Demos?
Not really, but I guess makers of these devices would be interested in this. But yeah, well, interesting spread of sensors. All right. With that said, before we move on to the last Q&A, here is I guess a list of for more information going forward. Questions are coming in. We'll not be able to answer all of them. So if you need to actually contact our panelists, we've given you their contact info and then some links on additional information that you may want to get to learn more about what we talked about today. All right, so with that said, I think we are in a position to move to our final Q&A session, so let's get things lined up. All right, so the first question, this is actually for you, AJ, and it is, I guess, what kind of testing facilities or what kind of features and testing equipment do you see or are required for testing out these autonomous these systems on autonomous vehicles or autonomous navigation systems? I'll let you say a little bit about that, AJ, if you will.
All right. Yes. Thank you. Yes, and this is one of the very frequently asked questions for us. The answer could be very broad. I'll try to keep it as focused as possible. So the answer really depends on what features you really want to test. So let's say, for example, if you're more interested in the corner cases of the area of simulation comes in very handy. Whereas if there's real world testing that you're interested in, you can as well do that depending on your application, depending on what parameter is the key for you guys. So both need to have repeatability, and we do offer solutions for both approaches, for having corner cases and having repeatability in real world environments. There's another dimension to this answer where the sensors might not just include navigation for GNSS, but it might include other sensors. So the test solution needs to include all these different sensors, as Curtis, Matt, and Chaminda have explained. It's no longer just one sensor, it's a combination of all of these. So simulating all of these is the key going forward. The second part of the question really talks about standards. There are a couple standards out there. There is an ISO standard 26262 for the safety. There is another for V2X coming up. So there you go.
Right. All right. Let's see. Thank you very much for that one. Chaminda, this one is for you, and it's actually about Locata, and it's how do you scale, I guess the Locata system in a cost-effective way, or how does it scale up?
Sure, yeah. So one of the things we are doing is with our next generation hardware, we are going frequency flexible. So let's say if a customer has a certain license to operate in a certain frequency, we may be able to, we can adapt to that. So that also gives us the opportunity to, the frequency flexibility gives us the opportunity to simplify the equipment, especially the antenna. So that can be done. So the cost can be made more affordable from the antenna side as well as the transmitter side, receiver side. And the other thing is, in my example, I showed the complex antenna in the user side. We can also make the complex antenna the transmit side. So that way the cost can be brought down as well. So you don't need a very complex antenna at the user end. So we're working on several fronts to make it more affordable, scalable.
Great, thank you, Chaminda. Next question. This one is for you, Matthew, and it's about. It's basically how would one or how should you characterize errors in the integrity analysis that you're doing for these autonomous vehicle applications? How do you model errors?
Wait, can you say that again, Demos?
Okay, so how would you characterize errors in the analysis that you've done for the I guess integrity and PHMI type of probability analysis that you showed? How do sensor errors get characterized, or how do they fit into that framework?
I just want to clarify, Demos, that this is the error. The question was asked in regards to artificial intelligence for
correct.
an AI.
Correct.
Yes. Okay.
Correct.
So just want to clarify that AI is not really used in the localization the characterization of localization errors. The AI is used for a lot of the path planning the path planning part of mobile robots, and in that sense, we don't focus on that in our research, but I think really the only way you can do that is through experimentation, and that is where that is why Waymo and all these other companies are talking about driving these large, 8 million miles and 6 billion miles in simulation. That's where that comes into play. And really, I don't know of any other technique other than sort of brute force when you're looking at AI and safety when it comes to mobile robots.
Okay. I mean, Curtis, Chaminda, anything you want to add to that, or?
Well, the only thing I would add is, in order for us to have confidence in the output of a vehicle localization problem, we really need to have confidence in the input. So I agree with Matthew that it's critical that we really characterize the quality and our confidence in whether it's LiDAR, camera, radar, GNSS, IMU, or map. We've made good progress, I would say, within GM about methods and parameters to look at carefully from those sensors so that we can confidently evaluate the quality of the inputs, but it's not, there's no easy solution, I would say, to the problem.
All right.
And to add to that,
go ahead.
To add to that, so as a sensor or as part of a system, Locata provides all the integrity, confidence information for that integration process. So we are just like another sensor, going with what Curtis was saying and what Matthew was saying. We provide all the confidence information for our measurements, for our output, just like a GPS receiver would. So we follow the same philosophy in that sense.
Okay. Excellent. All right. Let's see. Okay, questions are coming in fast and furious. So this one is for you, Curtis. You mentioned that GM, that the GM HD map is based on RTK. And the question is it feasible to extend and create these maps for urban areas where RTK availability might be intermittent? If not, are there alternatives to 10 centimeter and 95% confidence in urban areas?
Yeah, good question, and a perceptive question. So I'll answer that in two parts. My first response is we absolutely have to create high quality, high accuracy, absolutely localized maps in urban areas, so there's no getting around that. As far as the technology required to do that, there are alternatives to RTK, where a survey company, for example, wouldn't have to establish RTK base stations at regular intervals throughout a city. Some of those alternatives could be PPP corrections from a commercial source, such as Trimble, Novatel, Hexagon. There are a variety of PPP sources that can be obtained in real time. Another good alternative to RTK is post-processing. So there are government core stations located throughout the United States and Canada that can be used to create a precise map. We've tried that in GM with, I would say, pretty good success. So the way I'd answer the question in two parts is, first, we have to create that map and there's no alternative to it. But the good news is it doesn't necessarily have to be based on RTK. And we can use other technology when necessary.
All right. Okay, let's see. Let's move on. And this next question is going to be, let's see. It will be for you, Matthew, and it is. Can you? I mean, with the increase in GNSS, constellations out there, do you ever see a case where it's going to be possible to do these type of, autonomous vehicle navigations with the GNSS only and use other sensors just as for integrity monitoring?
Yeah, I think The answer would be generally no. We've done some work, my collaborator has done some work to look at, even once all the GNSS satellites are up and running in 2020, and there's places just in Chicago, which is a quick sort of back of the envelope simulation and study, and there's places in Chicago there where you still won't even get a lock on some streets from these satellites. Can you augment them? Yeah, I guess so. But I mean, in robotics, what we're looking at is can we operate in the environment with minimal augmentation or modification to that environment? That poses problems. Anytime we want to operate a field robot, and you're talking about modifying that environment, in general, it's not a good idea. What you want to do is to design that robot to work in that environment without modification. So I would say generally no, it's not going to happen.
All right. Chaminda and Curtis, anything you want to add to that?
No.
I would like to add one thing to that. So one of the applications of our multipath mitigation technology, correlator beamforming, we think can help to some extent, although it's not gonna. So instead of looking at reflected signals, we can enable the identification of direct signals, whatever is available. So if it's a narrow band of the sky between two lines of buildings, our technology can enable help in that sense, and that's where we are working with potential partners to apply correlator beamforming technology for GNSS. So that can potentially help to bring in more observations, not necessarily a full solution.
All right. And Curtis, did you have something you wanted to add to that?
Oh, I don't think I can add much to those comments, so I'm good.
All right. All right, next question. This one is for you, Curtis. Are there, I mean, are we, as you know, as this technology is developing, are there established performance standards, metrics for autonomous vehicle navigation solution that are considered by the automotive companies while testing their systems?
I guess the way I would answer that is we take our cues from an international standards organization specification. It's called ISO 26262. And that specification describes automotive safety integrity levels required for different levels of autonomous operation. Those levels range from 1 through 5. And as the level of competency for autonomous operation increases, the demands for safety ASIL protection also increase. So I'm not sure if I'm exactly answering the question, but if we have a fully autonomous car, level 5, that drives the need for careful functional safety reviews and audits of how we perform functions like redundancy. You know, if a sensor were to fail, how would we cope with that? It deals with hardware design issues such as memory fault detection and CPU issues that can arise in an embedded system. So the way that tends to be done in the auto industry is we look at the feature that we need to enable for the customer. We look at the consequences of a failure with that feature, and then trace that back to the protection levels that we need to drive in both the hardware and the software from a computer module that would support that function. So I hope that answers the question, but it's really ISO 26262 that has a strong role in the certification and development of an autonomous function.
All right, thanks, Curtis. Next one is for you, Chaminda. Can you say something about other RF-based positionings like cell phones, etc., and how does that complement Locata?
Sure. So I can particularly talk about cellular. I guess as I mentioned before, we look very much like a GNSS constellation with some important differences in that we are ground-based. We don't use atomic clocks, and multipath mitigation capabilities there with our proprietary technology. So we do see kind of two areas where we can mutually benefit if we can work with cellular industry, and we are working with potential partners to see if we can do this. Now, first one of them is correlated beamforming again, because no matter what, even if you come up with a good ranging capability, you still need to deal with multipath. So like I mentioned before, correlated beamforming technology can be implemented with the transmitter side with the complicated antenna. So so let's say if we can co-locate a locator transmitter with a cellular tower, we can enable ranging from our system, and we can potentially help in time synchronization as well. We have shown that we can time synchronize very precisely in our systems. We do that every day. So we do see some areas where it can be mutually beneficial with cellular ranging capability. But again, fundamentally, we are a ranging-based system, just like GNSS. So there's that difference.
All right, thank you. All right, so this next question, I'm going to direct it at you, Matthew, but I mean, if Curtis and Shaminda want to pipe in, you might as well. And it has to do with the answer to the first poll question of how much data collection is required to validate one of these systems. And one of the audience members is asking, do you have any comments, or do you want to add anything more to that, to the answer to that question?
That's a great question. I would think one of the poll answers was we can do it in simulation alone, and I just don't think that's possible at all. I think the number of years will probably be somewhere in between I think 2 and 3, which is between a year and 10 years. We can hopefully see an exponential increase in the number of test miles driven. So even though we may be in the order of millions right now, I think we can get up to 10 to hundreds of millions in the next, somewhere in the next 10 years or so. But you know, that said, I still would probably hop in a self-driving car before that happens. You know, I think we're not necessarily 10 years away from seeing these kinds of things.
Curtis, would you want to add to that?
I'll add a bit to that. So Matthew mentioned Google's Waymo division, their autonomous vehicle division. I would expect within the halls of Waymo, the leadership is looking at the number of miles that have already been driven, and I'm certain they're saying that's not enough. You know, we need to do more. Now, certainly there's a role for hardware-in-the-loop simulation. Certainly there's a role for looking at component performance in a controlled environment, and those activities for sure can reduce timelines and speed deployment to market for autonomous functions. But at the same time, you know, we need to remember that these are complicated systems, and the road environment is complicated and unpredictable, and there's really just no substitute for getting out there with a live vehicle in the wild. So as an automaker, I would say we just need to be creative and clever in defining the mixture of real world hands on the wheel or hands off the wheel driving, you know, versus intelligent and creative use of test equipment.
And as far as the question that could be done, I mean, the answer rather, that could be done all in simulation, your take on that?
I would not be employed if that was my attitude at GM. So
okay. Yeah. All right. Well, unfortunately, when you're having fun, time flies, and we're already at the end of our webinar time. Thanks for all the questions that came in from the audience. We could not answer all of them, but we tried to. So with that, I'm going to hand it over here to you, Lori, to take us to the closing.
All right, thanks, Demos. And folks, before we sign off, thank you to each of you for joining, and trust you found today's webinar to be of value. As well, special thanks to our distinguished panel members and our sponsor, Spirent, and co-hosts InsideGNSS and Inside Unmanned Systems. And again, thanks for joining. This is Lori Dearman saying, hope we see you on the next one. Bye for now.